I hope you'll forgive the rather large shadow on the piece of paper. This is due to quite a crude setup that I've managed to cobble together in order to make a video on paper rather than digitally. Now, we will be covering the same differential equation as was looked at before. This is exactly y prime minus alpha y equals f of x. Now, this time we are going to be using, and I will write here, eigenstuffs. By this I mean eigenvalues and eigenfunctions. This is a concept that stems from linear algebra, but it can find itself to be useful here. So we wish to solve this equation. This is what we call a linear differential equation. This is an ordinary differential equation. It's linear because the operator acting on y is linear. Now, what does this mean? It means that d over dx, we may write this left-hand side as d over dx minus alpha operating on y. And you can check that this is linear. That means if we, well, this holds for any linear differential operator, L of y1 plus y2 equals L of y1 plus L of y2, and L of, say, ky equals kl of y. So this is what we mean by linearity. Now, the idea is that since this is linear, we can study what are called the eigenfunctions of this operator. Now, an eigenfunction of an operator, suppose we have a linear operator L of phi of x equals lambda times phi of x. An eigenfunction is one that is scaled under application of the linear operator. Now, one could think of this as being a perspective of phi of x. Phi of x looks at L and it can't distinguish L and lambda. It sees L and it sees lambda. It can't tell the difference between the two. And so we wish to study the eigenfunction of, or the eigenfunctions, different ones associated to different values of lambda. By the way, this lambda is called the eigenvalue of this operator. We wish to study those eigenfunctions and eigenvalues. So we'll write phi sub lambda of x as the eigenfunction. So we'll write this, d over dx minus alpha times phi sub lambda of x equals lambda times phi sub lambda of x. Now, since alpha and lambda are both constants, we may move one to the other side and we end up with a rather simple differential equation. D over dx phi sub lambda of x equals alpha plus lambda phi sub lambda of x. This differential equation is solved by dividing by phi sub lambda of x, and we end up with the logarithmic derivative of phi sub lambda of x with respect to lambda equals alpha plus lambda. And we also see that this is, again, easily integrated. Both sides are integrated. The logarithm is removed by exponentiating, and we are left with something of the form phi sub lambda of x, it has a constant at the front. This isn't really relevant though. We'll just write e to the power of alpha plus lambda x. Technically, there should be a constant multiplying at the front, but this does turn out to be quite irrelevant. The power of studying the eigenfunctions is that when we can write a function as a linear combination of eigenfunctions, we can predictably apply this linear operator to it, or the linear operator being studied to it. So if we are able to write y as a linear combination of eigenfunctions, then we know how the operator acts on it. And if a linear transformation is invertible, then its inverse is also linear. And if we are able to write f as the sum of, as a linear sum of eigenfunctions, we may also apply the inverse and solve for y. So we suppose that y can be written in this way. So y of x equals, and here's a quite an important part. We have to talk about integrating over, it may be continuous space, but if it's not continuous, then we are actually summing, because a linear combination could be linear in the continuous or the discrete sense. And so we write a special integral. We'll write integral over a domain D, and the inside will be phi sub lambda of x, and then to encapsulate what we mean when we are writing it as a linear combination, and to really explain away the idea that it could be continuous, it could be discrete, we write, and these are functions, eigenfunctions of x, well, eigenfunctions of the operator, but we're summing them over lambda. So we will write d mu of lambda, and we will say that mu of lambda will also keep track of the weights for us, because it could be that we've got 1 of phi sub 5 of x and 3 of 5 sub pi of x, and we don't actually need to know what exactly those weights are. This will encapsulate all of it. Our next step would be to apply this linear operator. So we write d over dx minus alpha y of x equals. Now, since this is some sort of sum or integral, we may move any linear operator inside, and the linear operator acts on x, not on lambda, so we're not messing around with the integration variable here, or the weights, or the summation index. Simply, we may move this in. I will write it out in full though. D over dx minus alpha integral of over d of phi sub lambda of x d mu of x, which then equals the integral over the domain d over dx minus alpha phi sub lambda of x d mu of x. Pardon, I wrote d mu of x, I meant d mu of lambda. Now we know what this is, since by the definition of an eigenfunction, this should be exactly phi lambda multiplied by phi sub lambda of x, which we can write out as lambda times e to the alpha plus lambda x. Now, if we go back and substitute this expression in for phi sub lambda of x, we notice that alpha x, e to the power of alpha x, is independent of lambda. So we can write e to the alpha x integral over the domain D of e to the lambda x d mu of lambda. Now this integral is, I will just write it out again over here. We've got y prime minus alpha y. Remember, this is equal to f of x. So we will write f of x equals, and then inside we've got lambda e to the lambda x multiplied by e to the alpha x, which is independent of lambda. We may move that outside of the integral. So we have e to the alpha x times the integral over the domain D, and within the integral, the integrand will be lambda e to the power of lambda x d mu of lambda. Now, one has to notice something quite important. That is that lambda e to the lambda x is equal to the derivative with respect to x of e to the lambda x. We've got over here e to the power of lambda x, and so it seems that differentiating this section here, this integral here, which is part of the expression for y with respect to x, will output this lambda e to the lambda x. It will produce this lambda within the integral, and this is the integrand for part of f of x. We can write it like this, that d over dx of y of x times e to the negative alpha x equals f of x times e to the negative alpha x. I will repeat that just briefly, that f of x multiplied by e to the negative alpha x will result in this integral, y of x multiplied by e to the negative alpha x results in this integral, and this one is the derivative of this one with respect to x. Now all that remains is solving the integral itself. Well, sorry, solving this much simpler differential equation. This is done by integrating both sides and multiplying by the exponential. We'll do that here. Y of x equals e to the power of alpha x times the integral of, and I'll switch these for a reason that I won't explain here, but it's obviously the same. E to the power of negative alpha x times f of x dx. This is our solution. Now, I'll note that this looks odd. You've got x outside and you've got x inside. And what I mean by this is that this is the indefinite integral with respect to x. When solving such a differential equation, this must be evaluated first, and a constant of integration will be produced, which will then be multiplied by this e to the alpha x. And so it's very important that this is done first, and there is a way of writing this without having x as the dummy variable inside the integral. But though it's a dummy variable, we've got the same variable outside for writing it in a neat and short way. Were we to replace this with another variable, we'd have to evaluate it somewhere, which is a bit of a pain. And so this is the shorter, neater form, and it's produced quite naturally from our work. This is quite an interesting method, and I'll permit myself to talk a little about some of the other ways that one could apply this idea of writing a function as a sum of eigenfunctions. A very interesting example is applying this idea to the vector equation, well, the eigenvalue equation, eigenvector eigenvalue equation from linear algebra. We have mv equals lambda v. For all of the eigenvalues lambda of m and all of the eigenvectors v of m, really more the eigenvectors than the eigenvalues, we can write a different equation. We can write mv1 equals lambda 1 v1, mv2 equals lambda 2 v2, and so on. We may write mvn equals lambda n vn. And these are all column vectors. We can think of how the matrix acts on column vectors independently. When we multiply two matrices, the matrix on the left operates individually on each of the eigenvectors. That is to say that you can decompose a matrix into a sum of, in some way, a sum of eigenvectors. So we may write a matrix that looks like this, v1, v2, and this can be written where we're putting all the entries into the column. This can be written as v1 and then zeros all the way along. So 0, 0, 0, and zeros going that way too. Plus zeros, and this is quite an obvious idea, but it turns out to be quite powerful. Zeros and vn turns out to be quite powerful because we can apply the same logic as before, that m acting on the first will just produce the values lambda, and we can check this when we apply, we will just get lambda times the identity, since on this side we may write lambda v as being lambda I v. And so operation of the matrix acts very predictably on each of these, and perhaps I leave it as an exercise to the viewer to show that this leads to the ability to diagonalize matrices, and that's quite an interesting exploration. That's where I'll leave it.